Happy Friday, everyone, and welcome back to our Back to Basics series. Today, we're diving into a critical component that has powered the cable industry from its earliest days, the coaxial cable. Known for its reliability and efficiency, coaxial cable is often misunderstood despite its ubiquitous presence in our networks. Today, not only will we explore its fundamental properties like impedance, attenuation, and velocity of propagation, but we'll also offer a high-level overview of how these characteristics impact its performance. I'm Brady Volpe, your host and founder of the Volpe firm and Chief Product Officer of OpenVault. Joining us today to help unravel the mysteries of coax cable is the legendary Ron Hranac. With over 5 decades in the cable industry, a fellow member of the SCTE, co-founder and assistant board member of the SCTE's Rocky Mountain chapter, and inductee into the SCTE Hall of Fame, Ron brings a wealth of knowledge and experience that simply is unmatched. Ron, it's great to have you here again today. How's the connection looking on your end?
Thanks for the kind words, Brady, and happy Friday to you. Everything's looking good on this end, although I'm not looking forward to the heat of the afternoon for Denver. It's supposed to be 96 Fahrenheit today, which is pretty hot for here. Thankfully, the humidity is not what it is where you live.
Yeah, no, that's a scorcher. We're actually scheduled to get some nice dry weather in Atlanta this weekend, so looking forward to that.
Nice. Well, yeah, coaxial cable is an interesting topic, and it's been used in our industry going way, way, way back. So let me go ahead and share my screen and get us going here. So I want to share the entire screen. Click that, and bring this up and hit that button.
And folks, we already have a couple of questions queued up in the chat, so please do drop your questions there. We'll be getting to those questions very shortly.
All right. So here we go. The topic today, as Brady mentioned, is coaxial cable. And it's probably a good idea to start with an answer to this question. What is coaxial cable? From a very, very high level perspective, it can be envisioned as a 2-conductor transmission line. And it's made up of a center conductor, which is a round wire, and that can be either solid or stranded. But in the cable industry, we're dealing with solid center conductors. It's surrounded by some insulating material. It's a plastic or a foam material that's called a dielectric, and that keeps the center conductor supported in the center of the cable, and also helps to prevent it from shorting out against the shield. We don't want that. And then, speaking of the shield, that is the outer conductor or shield, and it surrounds the dielectric. And in many cases, in fact, probably more often than not, that shield is covered by a protective plastic jacket. So if we look at the slide here on the left side, we can see a side view of a piece of coaxial cable. That protective plastic jacket is usually either polyvinyl chloride, PVC, or polyethylene. The polyethylene or PE is often used in underground applications. And if you've ever worked on a cold winter day with underground drop cable that's got a PE jacket, it's a real bear to get connectors installed because that stuff is real hard. But the PVC jacket is used more often in overhead applications and indoor applications. Then you can see, moving left to right in the leftmost figure, we've got the outer conductor or shield, and then the dielectric, which is an insulating material, and then the center conductor, which the vast majority of the time in the cable industry is copper clad, either steel or aluminum. In the case of subscriber drop cable, it's copper clad steel, and in the case of hardline cable, it's copper clad aluminum. There is solid copper center conductor available for certain applications, but for most of what we deal with in the cable industry, it's really not necessary to have solid copper center conductor because skin effect keeps most of the RF at and near the surface, as we discussed in a previous session that we did on skin effect and skin depth. Yeah. So that extra copper, at least from an RF perspective, if you went with a solid copper center conductor, isn't really going to buy you any benefit.
Yeah, and we'll put a link to the skin effect video up in the top here so people can see that, because that was a great video.
Okay, let me move this
guy
a little bit here. In fact, let me hide that. All right, so here's an end view of this same piece of cable. And these are graphics I created in Visio, but you can see the copper-clad center conductor in the middle. There's the dielectric insulating material. the outer conductor or shield, which is basically a metal tube, a metallic tube, and then a protective plastic jacket on the outside of that. So that's the basic construction of coaxial cable, two conductors. So it is a two conductor transmission line. So why do we call it coaxial cable? And I give Brady grief,
or
and he gives me
coax
grief.
cable, and
He
if
likes
you're
to call
me,
it coax cable, but I call it coaxial cable. So why do we call it coaxial cable? And it refers to the circular cross sections of the center conductor and shield sharing the same geometric axis, hence coaxial. So here we can see the center conductor as a round conductor has its center point right there, its geometric axis, and the shield out here is that second conductor. It's also circular in cross section, and it's also sharing the same geometric axis. So that's why we call it coaxial cable.
to be
Shorthand,
technically correct.
yes, we call it coax. Brady calls it coax cable. I call it coax and coaxial cable, but there we are.
Let us know in the comments below what you think, coax, or what you say, coax or coaxial cable.
Yeah, and for me, it's coaxial cable, but I just said that. Okay, here are some of the probably more important characteristics and specifications that we in the cable industry are concerned with. There are certainly other parameters that I'm not going to cover here, but these are probably the ones most important to us. Impedance, well, that's 75 ohms for the cable industry, and I'm going to get into each one of these in a little bit more depth, but 75 ohms is the impedance that we use in the cable industry. Attenuation is very, very important, especially as we extend the downstream bandwidth of our cable networks to 1.2 gigahertz or 1.8 gigahertz. So attenuation is basically nothing more than loss or attenuation versus frequency, stated in decibels per some length or unit length. dB per 100 feet is very common, as is dB per 100 meters in Europe and elsewhere. And then velocity of propagation, we'll talk about this a little bit more in depth later on. That's typically in the 85% to 87% range. There are some exceptions to that. The old MC squared cable was up in the 92% range for velocity propagation. And if any of you have used communications cables, mostly 50 ohm impedance cables, but also early RG59 type cables that had what's called a solid poly dielectric or solid polyethylene. That's 66% velocity propagation. And then the so-called power feeder cable is up around 83%. And I'll show it some examples of at least a couple of these a little bit later on. DC loop resistance is something that's important, particularly if you're dealing with designing the network powering. You've got to know the loop resistance. That is the combination of the resistance of the center conductor over a specified length, typically 1,000 feet, and the shield over the same distance. So it's 1,000 feet here and per kilometer in other locations.
And later on, you're going to show us how to measure that. So,
I'll show you conceptually how it's measured, because the manufacturers measure it using laboratory grade instruments that can measure very, very low resistances. When you get down into less than an ohm resistance with a conventional home, I'll call it a consumer type ohm meter, the accuracy can be questionable. So that's why they use some really high end lab grade stuff for that. But yes, I'll show the fundamentals of how that's measured. Minimum bend radius, that's important for handling. You don't want to be kinking that cable too tightly going around a corner or tightening it up too much, because you can physically damage the cable. Common types, of course, we're all familiar with subscriber drop cables, head end cables, which are really a specialized type of drop cable, and then hardline cables that are hanging on the poles and buried underground. And then applications, well, overhead, underground, and indoor. So those are the main characteristics we're interested in. So let's start at the top of the list and talk about impedance.
Just real quickly. So, and we got a lot of questions popping up, but I think this is really relevant. So you mentioned, coax cable is 75 ohms. Wesley McGravy asked, do they use 50 ohm coax cable across the pond? So in Europe or anywhere like that, Ron, or is it always 75 ohm for coax?
In the cable industry, it's 75 ohms. 50 ohms you'll find used in broadcast, in two-way radio communications and that sort of thing. Ham radio uses 50 ohm coax, although 75 ohm coax is also used by some ham radio operators. I've used both, but in cable TV networks, it is 75 ohms. I'm surprised somebody didn't ask why we use 75 ohms instead of some other impedance. But
Yeah, well, we might touch on that. And Wesley also asked about the bend radius, no more than 10 times. But I think you're going to cover more on the bend
I've got
radius
some
later on.
examples, and
Perfect.
that boils down to read the manufacturer's instructions. All right, so what the heck is impedance? Let's define it. And I got to say, I'm going to warn everybody ahead of time. This gets a little bit gnarly when we talk about impedance because it's a bit more complicated than many people think. And I'm not going to do a deep dive into the lumped circuit equivalent in transmission lines. I mean, if you want to dig into that, there's a lot of good stuff that you can find with a Google search on transmission line basics,
modeling transmission line and stuff like that. So it gets very complicated very quick.
It's really complicated. And for those who have studied transmission lines in school, it's one of those things that can cause angst and gnashing of teeth. All right, so let's start with what the heck impedance is. The word itself, what does it mean from the perspective of our world of radio frequency signals? It is the combined opposition to alternating current, AC. And you might think, well, you mean the wall outlet voltage? No. Although impedance is certainly applicable there, but it's to alternating current, period, because our radio frequency signals are alternating current. All right, so continuing on. In a component, a circuit, device, or in the case of what we're talking about today, a transmission line that contains both resistance and reactance. And if we think about just resistance in the world of direct current, resistance is the opposition to current in a component circuit or whatever. But here, since we're dealing with alternating current, it's the combined opposition to alternating current that contains resistance and reactance. And we'll see why that's important a little bit later on and how it plays a role in this thing called complex impedance.
And so that's why we don't call, that's why we say impedance and not resistance when we're talking about 75 ohm. Because the 75 ohm, well, that's just resistance, but you're saying it's impedance.
Yeah.
And it's because there's an additional component, that complex component that you're talking about.
There is, and I've got a little graphic here that will illustrate the similarity to the world of direct current. But when we talk about impedance, it's represented typically by the symbol Z. Now, people call it a letter, but if you get into the world of the International System of Units, they call things like this letter Z a symbol. So I'm going to use the term symbol, Z, and it's expressed in ohms right there, just like
resistance.
Yeah. And there's a kind of a pie chart like looking thing that is commonly used in Ohm's law. Right. And you look at that and say, ooh, that looks familiar. Except notice that in the lower right corner of that, instead of an R,
there's a Z.
It's a Z.
Yes.
So here we're further defining impedance as the frequency domain ratio of voltage to current. So we can use this little chart here to say Z equals E divided by I, or I times Z equals E, and E, which is voltage, divided by Z equals I, the current. So there's the relationship. That looks a lot like Ohm's law. And the nice thing is, from that perspective, the math is largely the same, but it gets complex.
Oh, no, it's not simple?
No, complex, I don't mean it from, well, yeah, I guess you could say complex numbers are both not simple and complex.
Right.
All right. So, hey, speaking of complex, there we are. When we talk about impedance in an alternating current circuit, which, as I mentioned previously, covers the world of RF, it's a complex value. You say, what does that mean? And we're not going to get into complex numbers. Google it if you want. But here's the form of a complex number expressing complex impedance. And you see this Z equals R plus JX. There's complex impedance. You say, what on earth is that?
Okay. Doesn't look like resistance to me now.
Well, but it has resistance, and that's what the little R is for.
R.
So complex impedance includes resistance. That's the R in that equation. And we call that the real part of complex impedance. And then reactance is the X in that equation. And J is what's called an imaginary unit or imaginary number. So X is our reactance, either inductive reactance or capacitive reactance. And the J tells us that it's an imaginary number. Now, understand that when I say imaginary number, that does not mean fake or make believe something we're dreaming about. Now, some people might have nightmares about complex numbers, but that's a different topic. So this
Yeah.
tells us it's a complex number. And why do we say it's complex? The reason is because it often has both magnitude and phase. If it's just magnitude, then it's a simple number. It's just the resistance. But because phase comes into play, that makes things a little bit wonky. So we can then say that impedance really is a way to describe this concept of AC resistance. DC resistance is pretty straightforward, but you get into AC resistance, it gets really weird because of the presence of reactance in addition to resistance. So here's a plot that might help to clarify this a little bit. First of all, before I get into what this is showing, if we look just at the horizontal axis and imagine that this vertical axis does not exist, then this horizontal axis would be a way to express resistance, and it's only magnitude. That's all it is. It's just in ohms going from left to right. So down at the far left would be 0 ohms, and then we go up 10 ohms, 20 ohms, and so on. And it's only a horizontal axis number. But in the world of complex impedance, we have this reactance that comes into play. So we have to put that on what's called the imaginary axis, or the reactance axis, or in the case of quadrature amplitude modulation, we do the same thing with complex numbers. The horizontal axis is the I-axis for in phase, and the vertical axis is the Q or quadrature axis for quadrature. So we look at this and go, okay, so this plus J and then minus J, which indicates if it's positive, it's inductive reactance. So there's the X sub L, which is a shorthand for inductive reactance. Down here we've got X sub C, which is capacitive reactance. So that's minus. So the sign in this equation would change. If it's plus, then it's inductive reactance. If we put a minus in there, it indicates capacitive reactance. So let's think about a half-wave dipole. And we talked about that in one of our previous presentations. Yep. So a half-wave dipole, and we think of a half-wave dipole in free space, it's a thin dipole, has a complex impedance of Z equals 73.2 plus J 45 or 42.5 ohms. And you look at that and say, well, how on earth can we deal with that or understand that? And if we go to this little graph up here, we've got 73.2 ohms on the resistance scale. That's the real number. So we go over here to 73.2 on the horizontal axis, and that's right about there. So that's at this point. And then the plus J 42.5. And remember, the J tells us that we're dealing with reactance here, or the imaginary part of this. So it's 42.5 ohms, but it's plus. So we go up to 42.5, which is right there on the vertical axis. Remember, if this were capacitive reactance, it would be a minus sign and we would go down. But where this one goes up and this one goes across, the two plot right there. So that little dot is what this formula is telling us. This little dot is 73.2 plus J 42.5 ohms. And then you can express, and this is a Cartesian plot or a rectangular plot. You can also do what's called a polar plot of impedance. So you plot this same thing, and then you draw a vector from right here up to here. And then you would state this impedance based on the length of the vector. So it works out, in this case, it's 80-something ohms at an angle of whatever the angle is relative to this horizontal line. And an example of that is in the SCTE math document, which is where this graph came from. So it shows it that way. And then you can also plot it on a Smith chart, which I'm not going to talk about at all today, other than just saying
that gives you your vector, Victor. James Long mentions that he says, and because Euler's formula makes it easy to convert to a cosine formula. So he's really talking about the relationship between cosine, phase, magnitude, and what we're seeing on here.
And that's where we said this stuff gets complex.
Yes, it does, very quickly. My brain hurts now, Ron, thinking about this. Let's take a moment to cover some of the questions that we have in the chat here. Hank Yon says, hi, Ron and Brady. Can multiple impedance mismatches create a suck out around 1 gigahertz And is it possible to see those mismatches with a normal 1 nanosecond pulse width TDR? Your
Well,
thoughts there, Ron?
the answer to the first question is yes. In fact, when we measure a parameter in coaxial cable called structural return loss, which I don't get into in this presentation, but it's structural return loss gives us an idea of multiple repetitive impedance discontinuities that are evenly spaced, that can result in what's called an SRL, or structural return loss spike, on a plot of structural return loss. And then when you convert that to the frequency domain, it shows up as a suck out in the frequency response through that cable. And manufacturers have gone to great lengths to try to keep the structural return loss, or well, actually to keep the those microscopic impedance mismatches, the repetitive ones, down to a dull roar, so that we don't see these structural return loss spikes and then the suckouts. But with respect to a gigahertz, you'd need spacing at a half wavelength, that is repetitive impedance discontinuities at a half wavelength, to produce a suck out at a gigahertz. And the answer is, so yes, you could. So a wavelength at a gigahertz is what, 30, what is it? About 30 centimeters roughly. So half of that, so spaced about 15 centimeters apart, and that's, I have to convert that to inches, what, 7 inches or something like that. Let me see here.
Get the calculator quick.
15, 2.54 divide. Now, okay, let's call it 6 inches. Then could a TDR with a 1 nanosecond pulse width find or see those? And I'm going to say the answer is maybe, because if the spacing between the suckouts is about 6 inches, and it's actually going to be slightly less than that, you're only dealing with basically 5 inches of cable, and the propagation delay through 5 inches of cable is a little over a nanosecond per foot. So it's going to be kind of iffy whether a 1 nanosecond pulse width on a TDR will show that kind of resolution.
Yeah,
I think you'd have to play with it and see. Ideally, you'd probably want something narrower than a nanosecond if you could get it.
Yeah. So, shout out to Billy Williams there. Good to see you. And he did ask it, because you mentioned why no one asked why not 50 ohms, or why do we do 75 ohms coax cable? Why not 50 ohms? So, Ron, why is it 75 ohms?
It's a really good question, and we need to go back to some work done by Bell Labs decades ago, when they characterized in a laboratory, based on a whole bunch of measurements of different impedances of coaxial cable. And there's some graphs that are plotted, you can find them online, that show the impedance for the best power handling capability, the impedance for the best attenuation performance, and this is assuming the cable has the same physical outside diameter and so on. And anyway, so you find that the best power handling capability is somewhere in the 30-ish ohms range, and the best attenuation performance is up around 77 ohms. And as you go higher in impedance, the center conductor, for a given outside diameter being fixed, the center conductor diameter has to be smaller.
Get smaller, yeah.
But the communications industry and broadcast industry picked something that was kind of the geometric mean of those two. And it came out about 52 ohms, as I recall. So that's why you see 52 ohm coax out there. But the communications and broadcast world landed on 50 ohms. And when it comes to 75 ohms, you say, well, why did the cable industry choose 75 ohms? And in large part, that has to do with a couple things. And there are a couple stories out there as to why that is. But one of them is that in the early 1950s, there was a lot of military surplus 75 ohm coaxial cable available on the market for very low cost. And in those early days, the cable industry was stringing up RG11. And in those days, it really was RG11. It was mil-spec 75 or 72 ohm coaxial cable, depending. But this stuff was available on the surplus market. You might think, well, why would the military use 75 ohm coax? And the reason there is, and keep in mind that for a given size, the center conductor diameter is smaller than the same size coax that has an impedance of 50 ohms. So if you think about miles of coaxial cable strung around, say, a battleship or an airplane, weight can be an issue.
Very
So by
important.
going with a smaller center conductor, you reduce the weight some. So the military would have an interest in reducing weight to the extent possible. They use that 75 ohm coax. Now the other is because 75 ohm coax is real close to that point on that Bell Labs curve of attenuation, optimum attenuation performance for a given size cable. For the cable industry, in our early days of long cascades of amplifiers in those tree and branch networks, if you could think about it, if you could have coaxial cable that had lower attenuation per unit length, the 75 ohm coax would have lower attenuation. That means the amplifiers could be spaced farther
Further
apart,
you can go.
and you wouldn't need quite as many in cascade. Now, it's not a big difference, but every little bit helps. So those are the two main reasons why the cable industry uses 75 ohms.
Yeah, I mean, the first story I've always heard that it's kind of like that optimal resistance, but I never knew that we started off as an industry using surplus cable from the
Yeah,
military. That's
big
really
time. Big
intriguing.
time. Yep.
Very intriguing.
All right. So let's talk a little bit more about this characteristic impedance stuff. And this is pretty important. Not only, well, I'll show you a formula here that we use to calculate this. But the characteristic impedance, which we call Z subscript 0, is expressed in ohms. And I talked about impedance being expressed in ohms earlier. And here it's important to understand that it's related to the ratio of the inside diameter of the shield, so that's this big D, to the outside diameter of the center conductor, that's the little d. And some of this goes back to another approximation of characteristic impedance, or I think what's called surge impedance, is the square root of inductance over capacitance. I'm not going to go there, but I just wanted to mention that. But anyway, so this physical dimension relationship is a very important part of the impedance of cable, as is the dielectric constant epsilon, which represents relative permittivity of the insulating material that separates those two conductors. Now, if the ratio of D to D changes, and think of a ding in the shield of the cable, like I show
Little
here,
dent.
guess what? The dent in the cable lowers the impedance of the cable where that dent is, because the ratio has changed. So the shield is closer to the center conductor, or in effect, the center conductor diameter has increased relative to the diameter of the shield. So what happens is, in this example where the cable's been damaged, the impedance is less.
And I suspect that's a bad thing, Ron.
That's, well, unless you intentionally want it like that, but I would say, yeah, it's probably a bad thing. That's why we say don't ding your cable, don't kink it when you wrap it around corners, all those things, because it can damage the cable and change the impedance.
Yeah.
All right, there's a formula. Yes,
Course.
and people say, why we don't use math in cable TV when we're out in the field doing trouble calls or installs. Well, that's true, you don't, but it's important to understand that the foundation of everything we do in this business has math in it. And for more about the math of cables, take a look at the what we call the SCTE math document, SCTE 270 2021 R1. You can download it from the SCTE standards webpage. All right, there's the formula that you can use to calculate the impedance of coaxial cable. And we've got some numbers in here. So there's the ratio that we talked about of D to D. And there's, in this case, is the square root of the dielectric constant of the insulating material. So this tells you if this ratio changes over here.
Meaning if you dent your coax or kink your coax or overbend it, that you're changing your ratio.
And if the dielectric constant changes, so think water getting into the dielectric.
Yeah, water and coax is not
that
good.
That changes the dielectric constant and changes the impedance and also the attenuation in that case. Now, here's an example. Let's take an example of half-inch hardline cable. It's got a published velocity propagation of 87% or velocity factor 0.87. A little later on, I'll show you the formula that relates the velocity factor to dielectric constant, which in this case is about 1.32. So you plug these dimensions, and the 0.109 center conductor diameter, the 0.452 inside diameter of the shield. These are published on spec sheets for coax. Velocity propagation is usually published. What you don't usually find in spec sheets is the dielectric constant, but it's easy to calculate. So you plug all these numbers into this formula, and you get a calculated impedance, in this case, of a little over 74 ohms. And you say, well, why isn't it exactly 75? Well, it's actually within the plus or minus 2 ohm spec of coaxial cable, of hardline cable. So this is within less than an ohm of the actual. And the chemistry of the dielectric is such that the velocity factor is probably more of a nominal value. And they're paying really close attention to controlling this. But that gets into proprietary stuff going on with the coax manufacturers to ensure better uniformity throughout the length of the cable.
The secret sauce.
The secret sauce.
Yes.
Now, I need you to imagine some things here for a minute. I know we're spending a lot of time on impedance, but this is a pretty important one. Then the others will go a little bit faster. Let's imagine our piece of half-inch hardline, same physical dimensions, but we don't have a foam dielectric in there. Of course, right away you say, "Come on, Ron, that center conductor is going to fall down and touch the shield." But imagine that we don't need to support this center conductor. It's just going to kind of float there, right in the center, but the dielectric is air,
okay,
rather than our foam material. So if we start with air, the velocity factor works out to 0.9997. It's almost 100 or almost 1, and the dielectric constant is 1.000, and then some numbers there. This number is actually the dielectric constant of air, and I think that's a standard number. I think it was, if I remember right, sea level at a certain temperature and so on. But that gives you this velocity factor. If this were a vacuum instead, this would be 1 and this would be 1 in both sides. We crunch the numbers, and the impedance of this coax with an air dielectric is a little over 85 ohms.
Okay.
As soon as we put that foam dielectric in there that has that dielectric constant of 1.32 or a velocity factor of 0.87,
we get 75 ohms.
Basically 75 ohms. They've noticed the impedance drops. It goes from 85 ohms to slightly less than 74 ohms uncalculated. Recently, there was a discussion in one of the cable TV technical forums on Facebook, and somebody had asked a question about what's the velocity of propagation of 625 feeder cable. In this case, it's the CommScope 625 feeder cable, and it's not in the spec sheet, which kind of surprised me. They list the dimensions, so there's the dimensions of the center conductor and the shield. And the impedance is listed at 23 ohms, and people were throwing numbers all over the place. And well, it's this number, it's that number. So I started with 23 ohms and then worked backwards to get a velocity factor of 0.83, and then plug this number, which you convert this to dielectric constant to 1.205, and then plug that and these numbers into that formula that I showed you a little bit earlier, and you get 22.9 ohms. So basically 23 ohms. So that says the velocity factor is 0.83, or the velocity propagation is 83%. And I was curious about that because somebody said that a TDR manufacturer talked to somebody at CommScope, and they said it was 66 ohms. And I said, that math doesn't work. You can't have, if it's a foam dielectric, and with these physical dimensions and the impedance of 23 ohms, it can't be 66% velocity propagation. So I contacted CommScope directly, and they said 83%. So my calculated number was in agreement with what CommScope told me. So there we are. So somebody wanted this because they needed to know the velocity propagation to plug into a TDR so they could troubleshoot some cable damage in their power. All right.
Billy Williams commented, he said, the lovely air gap coax for your first image there. He liked that. And he said, I saw the post as well. And he said, I tried to find that spec, but was unable. So yeah, he had the same thing. And I want to comment back. James Long had mentioned when we were talking about the history of why it's 75 ohm coax, he said, the funniest possible answer to why 75 ohm, because it was cheap.
Well, so. Yeah. I mean, think about it. Military surplus cable is available after World War II, yeah, and a lot of it was available. Why not use it? Think of the entrepreneurs who were building the very early cable networks in the 50s, late 40s, early 50s. They want to save money to the extent they can. If there's military surplus cables available, use it.
Yes. James Long says he just calls it tubing.
Yeah.
Rather than coax or coaxial.
Yeah.
We got another one out there.
Let's move on.
Not a guy like me.
Yeah. All right, attenuation's a biggie. This is something that we pay attention to because we need to know what the attenuation is to make sure that we can design and build our cable networks properly. So the table on the right side of the chart is based on published specs. This is dB per 100 feet for Series 6 drop cable. Notice I didn't call it RG6. It ain't RG6. We don't use RG cables. Yes, we call them that, but they're
Where did
not.
RG come from, Ron? Do you know that?
Um, I wrote an article for, I think it was International Cable several years ago, and I did some research trying to figure out, and people say radio grade and radio guide, and I'm not convinced that's true because the information I got suggested it was random letters that the military used.
Back to the
Well, because
military
they have,
again.
well, military, that's what it was.
Yeah.
RG was a mil spec designation. They don't use RG anymore in the military. They changed it to something else. I was looking it up here a while back. But they used all kinds of designations for mil spec products. And they had it for connectors and cables and wire and everything you could think of. And I had talked to somebody, and this goes back to the 90s, about this. And they said it was, in fact, a random 2-letter designation. But for whatever reason, the folklore, and maybe it's true, maybe it's not, says RG is radio grade or radio guide. But anyway, it's a mil spec designation. And it's stuck around, even though it hasn't. We haven't used mil spec cable for decades.
Sounds plausible, sounds believable, and people today still say RG11, RG6. It's still common.
It ain't. All right, so this is Series 6 cable. So the table on the right is right from the published specs for Series 6 cable, up from 5 megahertz up to 1.8, or just about 1.8 gigahertz. So I took these numbers, put them into an Excel spreadsheet, and got this graph. So this shows in the graph here the attenuation, and you can see it's not a straight line or a nearly straight line like you'd have with a splitter or a directional coupler, but it slopes downward. And we talked about this in our skin effect presentation and why attenuation is higher at higher frequencies. It's largely because of the skin effect and the effective cross section of the cable, resulting in an increase in effective AC resistance at higher frequencies. The dielectric also plays a role, by the way, especially at the higher frequencies. So the combination of the dielectric loss and the metallic losses are what gives us this frequency characteristic, or attenuation characteristic versus frequency. Okay, now an important point, and I want to thank Tom Coltsey for this wording. He had helped review my article for Broadband Library on loss, and he suggested this be added to it. So I thought this is a really important point. So the cable loss at any frequency is proportional to the length of the cable. So if you've got a 200-foot length of coax, it's going to have twice the loss in dB as a 100-foot length of the same cable at the same frequency. And if you have a 300-foot length of the same cable at the same frequency, it's 3 times the loss as a 100-foot length of the same cable, and so on. Now, how do you calculate coax at a given frequency? Because you look at the spec sheets and it's dB per 100 feet or dB per kilometer or whatever. So here's how you do it. And there's a formula. So let's say we've got some subscriber drop cable, got a 150-foot length of it, and you're trying to figure out the attenuation at 750 megahertz. This is, of course, without measuring it. I mean, yeah, you could measure it, but how do you know your measurement's right? What should it be? So if the published spec for attenuation at 750 megahertz is 5.65 dB per 100 feet, what's the attenuation in 150 feet of that cable? Well, there's the formula. So it's 5.65 dB divided by 100 times 150 feet, and you get about 8.5 dB. So that's how you do it. So
pretty simple.
You plug in into the numerator of this little guy right here the attenuation per 100 feet at the frequency of interest, and then over here to the right of that, you multiply it by the actual length of the cable. So the 100 down here is per 100 feet, and you plug it in here, you crank the numbers. It's very easy to do. In fact, if you do this mentally, you could say 150 divided by 100 is 1.5, and then do 1.5 times 1.65, you get the same number. But I think this makes a little bit more sense. So this is the formula you can use to figure out the attenuation through any length of coax if you know the attenuation per 100 feet.
Now, this used to be in the little pocket handbooks, little pocket guides that we would get to calculate coax cable, the loss per 100 feet of coax cable from even different vendors.
Yeah.
But we don't get those pocket guides anymore when we go to trade shows. So, do you have a reference that people can go to, or you just say, just use this formula, Ron?
Well, I'd use this formula, and I don't remember. I don't think we put this formula in the SCTE math document, but using what's in the math document, you can certainly calculate it.
Yep.
But here it is.
Yeah, I think I should.
But you're right. It's a shame those little pocket books
I
aren't
love
available.
those pocket guides. I still have
Oh,
some.
I do too. I donated most of my collection to the Cable Center, but they're wonderful. All right, let's move on. Velocity factor and velocity propagation, they're pretty important. They're on a spec sheet. You might wonder initially, well, why am I as a tech concerned about these numbers? Well, you might use them to calculate transit delay through some length of coax between 2 points, for example, between a CMTS and the head end or hub and the input to a cable modem. And you may not do that very often, but that's one application. But probably more commonly, you're going to probably need to use one of these numbers to configure your TDR, your time domain reflectometer, if you're going to troubleshoot plant. You need to know the velocity of propagation or velocity factor of the coax. Got to program it into your TDR, and then you can do testing in your plant for damage and so on. But you got to know that number for that. So here's an example. The assumption here is pretty easy. 1,000 feet of hardline coax, the velocity factor is 0.87. Then you got 100 feet of drop cable, velocity factor is 0.85. And you say, well, wait, that's two different numbers. How do I figure that out? Okay, one-way transit delay, 1,000 feet times 1.17 nanosecond per foot. I'll show you where you get that number a little bit later. Plus 100 feet, and there's your drop cable, times 1.2 nanoseconds per foot. And there again, you might say, well, how do you get that for drop cable? I'll show you later. Equals a total transit delay. In other words, it's how long it takes the RF to go from here to here. It's 1,290 nanoseconds or 1.29 microseconds. So that's how you can calculate that.
Perfect. Another good equation. And Ron, I was just informed on a chat by Grab a Sandwich and Billy Williams. Thank you guys. That the Pocket Guides are now an app. I was not aware of this app, but I am going to go take a look at that after this show and download that app because it will be very handy to have on my phone.
Yes. All right. So let's define these terms then. Velocity factor is the ratio in decimal form of the speed of an electromagnetic signal, so think RF, traveling through coaxial cable compared to the speed of light in a vacuum. And as mentioned earlier, the common velocity factor for hardline coax is 0.87, and for drop cable it's 0.85. So mathematically, okay, there's more of that darn math. Velocity factor is C divided by C subscript 0, where C is the speed of the electromagnetic signal traveling through the coax, and C sub 0 is the speed of light in a vacuum. And these two C's have to be in the same units. For example,
really, that just tells you the velocity of propagation. Well, it tells you the
velocity factor. Velocity of propagation is just velocity factor expressed as a percentage rather than decimal form. That's it. That's all. So there's another, and this gets us back to remember I had to work backwards on to figure out the dielectric constant of that power cable and stuff. Well, velocity factor is related to dielectric constant by this formula. So pretty simple. This is right out of the SCTE math document. Very simple. And then dielectric constant, I mentioned that. I said, okay, well, what's that? Well, this gets a little gnarly, but I just want to mention it here. It's a parameter that applies to the dielectric, the insulating material in coax, and typically refers to relative permittivity. I've got a little asterisk there, and I'm going to define that in a minute. And relative permittivity, while the term is still used, has been replaced by something called relative static permittivity, but I'll just use relative permittivity here. So the dielectric constant then is related to the cable's velocity factor using this formula. So 1 divided by the square of the velocity factor gives you the dielectric constant. So pretty straightforward stuff. So if we've got a hardline coax with a velocity factor of 0.87, you plug that into that little formula, and it gives you a dielectric constant of about 1.32. So that tells you that anything that changes that dielectric constant, like water in the dielectric, is going to change the impedance and, unfortunately, the attenuation. Okay, permittivity, read and weep. This is another one of those things that makes you go, that makes my head hurt. So I'm not even going to bother to read that. But relative permittivity, which is up here, is the ratio of the permittivity of the dielectric to that of a vacuum. So that's all.
Kind of impacts the how easily or not easily the electromagnetic field can transfer or can propagate through the medium.
Yeah, yeah. All right, then velocity propagation, that's just the velocity factor expressed as a percentage. So the velocity factor is 0.87, velocity propagation is 87%. And all that means is the RF is zipping through the coax at 87% of the speed of light in a vacuum. That's all that means. Oh yeah, more math. Easy though, I promise. This is real easy. So if the cable's got a velocity propagation of 87%, that's hardline cable in most cases. The RF is traveling through that cable, and here's how you figure out the speed. So speed of light in feet per second is this number here,
It's a pretty fast
983
number.
million and change, times 0.87. I'm still fast.
Yes.
So the RF is going through the coax at 855 million and change feet per second. Or if you take the reciprocal of that, 1 divided by that number, you get, there's that nanosecond per foot, 1.17 nanosecond per foot. If you do the same thing for drop cable with a VP of 85%, then you get the 1.20 nanosecond per foot. So that's how you calculate that. Easy stuff.
Simple.
And
simple.
Well, it is. I mean, this is actually pretty simple, pretty straightforward.
Fortunately, we typically have software that does all this for us.
Well, yeah, you can put it in a spreadsheet if you want,
Yeah.
or be a nerd like me and remember these numbers and formulas. But anyway, all right, so let's move on to DC loop resistance. And I mentioned earlier that DC loop resistance is important when it comes to designing the powering for your cable network, because you want to know what the voltage drop is through the coax. And in order to do that or sort that out, you need to know what the resistance of the metallic conductors are in the coax. And here we're talking about DC resistance that we would measure with a conventional ohm meter, or in the case of a coax manufacturer, a lab grade ohm meter that can measure very low resistance values. So if we look at a spec sheet for half-inch cable, we might see numbers like this, and they'll publish the end-to-end resistance of 1,000 feet of the center conductor. So in this case, it's 1.35 ohms. That's measured end-to-end. And then for the shield, also measured end-to-end over that same 1,000 feet, it's 0.37 ohms. And now you get down into that low resistance number, and your conventional ohm meter is going to be kind of iffy on its accuracy, especially because you've got to take into account the leads and the other stuff. And so it's the lab grade stuff is what's used by the manufacturers to really characterize this. So for the loop resistance, just imagine taking that 1,000-foot piece of cable, you short circuit the center conductor and shield at the far end, and then you measure between the shield and center conductor with your ohm meter, and there's your loop resistance. That's it. That's what it is.
Now, would this test be useful for anything, Ron? Say if I had a spool of cable in the head end and I wanted to know if that spool of cable had any damage to it?
Your conventional multimeter is probably not going to be accurate enough to determine that.
Yep.
I'd say you're better off using a TDR.
Agreed. TDR is always the best way to test if you have any small dings or dents or anything like that in the coax cable that's actually going to cause damage. I've seen people try to use a multimeter to say whether or not a piece of coax cable has any damage to it, but I don't think it's going to actually yield any valid results.
No, I would say no. I mean, you can use it for toning out cables in a multiple dwelling unit, like an apartment complex. That's good for that. You might be able to tell that, oh, wait a minute, I put a 75 ohm terminator on the end of the cable at the outlet in the house, and I'm measuring, and I got an open circuit. I can't measure 75 ohms. So that could say, the cable's probably been cut or something.
Yes.
Or something like that. And if there's a splitter in line and it doesn't have the DC blocking or the blocking capacitors in series with it, you're going to be measuring through the splitter, and that gives you some very low resistance readings on the order of fractions of an ohm. So that can be misleading too. All right, bend radius, minimum bend radius. It's just an important parameter. It's in the spec sheet just for handling the cable. Bottom line is, don't kink or bend the cable smaller than the specified minimum, because cable damage can occur. You kink the cable, change the impedance where you kinked it. And here's a couple examples of published minimum bend radius numbers. For half-inch jacketed hardline, about 3.5 inches. And for Series 6 drop, and happens to be tri-shield, it's 1 inch. Now, this is the minimum bend radius. That would be the length of this little arrow here. Now, obviously, this is not to scale, but it just illustrates the concept. So pay attention to the specs and don't bend it too tightly because you can damage the cable.
And that goes back to Wesley's question on no more than 10 times the diameter of the cable based on the bend radius. So I think that kind of goes back to your original response. Like, it really depends. Check with the
It depends.
manufacturer.
Check the spec sheet.
Yep.
Go by what the manufacturer says. All right, typical types of drop cable: Series 59, Series 6, Series 11. There used to be a 611 that was kind of an in-between, and some called it RG7. But remember, we don't use RG cables. Series 59, Series 6, Series 11, and head-end cable, which is typically a Series 59 quad shield cable, and it might have a silver-plated center conductor instead of copper-clad, and it also might have a silver plated braid, but it's basically a Series 59 type cable.
And what does a quad shield mean, and why would we need quad shield in the head end versus non-quad shield in the head end?
Well, it's not necessarily just a head end. The quad shield refers, and I talk about that in a minute, just to the number of shields in the drop cable. Okay. So in this case, there are actually four shields. With hardline, it's one shield, and in the case of this, there's four shields to give better shielding performance. And hardline, well, there's some pictures of hardline that I just snapped that with a camera, so you can see unjacketed hardline cable in the top, jacketed 1/2-inch cable on the bottom, and then the drop cable up at the top is a piece of Series 6 cable that's prepped for an F connector, and I did that here with the prep tool that I used. Okay, applications: overhead. You can use unjacketed cable or bare aluminum like this. Word of caution: don't use unjacketed cable in environments where corrosion can be a problem, such as coastal areas, or in environments where you've got industrial pollution, because it can eat through that unjacketed shield. Quick war story. Back in the 90s, the company I worked for at the time, it was Jones, bought the cable system in Castro Valley, California, which is near the San Francisco Bay. And it was a dual plant, and the hard line was unjacketed. Whoever had built the system, probably in the 60s, decided to skimp on the cable, and they did not use jacketed cable. And the shield of that cable was constantly cracking. It was thin and brittle like eggshell because of the severe corrosion of the outer conductor. They should have used
saltwater's so brutal.
Saltwater's horrible on that stuff, and that was a good example of it. Jacketed cable. This is typically used. Well, as far as I know, used on most, if not all, drop cable. And for hardline cable, this is good if you're in an environment where you're in a coastal environment or in an area where you've got industrial pollution, and in underground applications. We'll talk about that in just a moment. And then messenger cable, sometimes called figure 8. This applies to both drop and hardline. All overhead drops should be messenger, period. Yep. That's Ron's recommendation. For hardline cable, the figure 8 has been commonly used in smaller rural systems where they didn't want to string up strand and then lash the cable, the hardline to it. It becomes all in one. The self-support messenger does away with the need for strand. Of course, you don't lash anything, but it's got its own construction issues and techniques, but that's been used too. But it is available.
And for anyone who doesn't know, the messenger cable just has a strand of wire attached to the coax cable, so that strand of wire can support the weight of the coax cable and not sag when it's hung aerially. Correct, Ron?
Well, yeah, and it's important to note that messenger wire is not actually touching the shield of the coax.
Right.
It is separate, and it is when the jacketing is applied, it is this thing runs parallel to it, so there's a thin web of plastic between the jacket of the cable and the jacket that's around the messenger. But yes, it's right there, and it basically supports the cable. Now, corrosion protection. Most, if not all, manufacturers have got versions of cable with corrosion inhibitor used for overhead applications or in indoor applications or on the house applications. There's also flooding compound used for cables in underground application. Never use flooded cable that's intended for underground applications in overhead applications. Don't do it. Guess what happens if you use it in overhead applications? Flooding compound will eventually drip out, and if it drips on somebody's car parked on the street, not good.
Messy stuff.
Don't use it indoors because there have been cases where the flooding compound, somebody used flooded cable inside the house, it dripped out onto the carpet. Don't do it. All right. Now, speaking of flooded cable, and it's kind of hard to see in the figure here, but you can see a little layer of this molasses-like flooding or filling compound. The idea is that if you get a pinhole in the jacket or a tiny bit of damage to the jacket, the flooding compound will flow to that and help prevent water from getting into the cable and damaging the shield. Obviously, if the jacket is damaged too much, even the flooding compound is not going to work. My suggestion, use flooded cable for all underground applications, period. No exceptions. Even if it's in conduit or direct buried, always use flooded cable for underground. Armored cable, this stuff's a bear to work with. There's a cutaway on the cable here you can see, and I think it's a stainless steel wrap around the cable. So if I remember right, it's a jacket that's first put on the cable, then the armor goes on top of that, and there's probably flooding compound in there, then another jacket. This gives extra protection. It's good for direct burial. This stuff can cut the daylights out of your hands if you're not careful when you're cutting the cable to prepare for a connector. I have cut connectors onto this kind of cable, and it is a pain in the patootie, but it is available. All right, indoor. We've got typically dual shield, tri-shield, which means 3 shields, or quad shield, which means 4 shield designs are available, with or without corrosion inhibitor. And as I mentioned before, never use flooded drop cable intended for the underground applications inside of the customer premises. Depending on what's going on in the environment, head ends, got a lot of RF floating around, so you probably want to use that quad shield head end cable. Some over-the-air environments, maybe close to cell phone sites and other things, tri-shield and quad shield are better because they give you more shielding, so you've got extra shielding on the drop cable. So wrapping it up, and I've got some graphics that show how cable is manufactured. We'll get to after I get to this little summary here. So coaxial cable has been used in the cable industry's networks going way back, almost the earliest days. I think the Ed Parsons system in Astoria, Oregon, if I remember right, strung 300 ohm type twin lead from roof to roof, and then other systems started using the coax that had become available on the surplus market. So we've used coax going way back, way back. I have to say, you think of the manufacture of coaxial cable as being kind of an industrial process. It's actually very complicated, very sophisticated, and they've got really careful control of line speeds and mechanical processes and pulley spacing and pulley diameters and all this stuff. They use specialized dielectric chemistry. There's automated test and measurement. They've refined packaging. So think like the hub in a reel. If you've got planks that the big reels used to use, the inside wrap around the hub can get dings in it because of the planks. So they went with a smooth drum in these cables to help improve the performance of the cable over wider frequency ranges.
Well, being able to maintain a consistent impedance without impedance mismatches has to be extraordinarily difficult.
It is. You want more uniform impedance throughout the length of the cable. Attenuation needs to be where it's supposed to be. And other characteristics. And these days they're speccing cable up to 3 gigahertz.
That's amazing.
So it's amazing. All right. I'll just show this for a moment, and I see we're coming up a couple minutes away from the top of the hour.
We do have a few more. Oh, well, we got a couple more questions in here, Ron. David Coble said, wouldn't it be better to measure the DC loop resistance using a Kelvin connection instead?
A Kelvin connection? I'm not familiar with that, so I'm going to say that at least based on what I saw at the coaxial cable manufacturers, they were using lab-grade instrumentation to measure the resistance of the conductors.
Billy Williams says they've been using flooded cable in hardline aerial coax for an aerial plan for years, mainly to deter squirrel chews. I find that interesting because they actually make special cable to deter squirrel chews.
It seems to me that they tried some capsaicin and other stuff under the jacket, and in some markets the squirrels love the stuff.
It
doesn't deter them; they're gonna chew it, and
Grab a Sandwich says, care to touch on situations where houses have an open neutral on the power?
Well, not directly related to coax, other than the fact that if there's an open neutral at the side of the house, the shield of the coax is probably going to become the neutral conductor for the house, and you can get excess current traveling through that coax and actually melt the cable. Yep. So, when you see that,
it could also become an electrical hazard for the technician, right?
It's electrical hazard at that point. Don't touch anything if you got a burned up drop because of that. They need to get an electrician out there to see what's going on. If it's open neutral in the customer premises electrical, like the electrical panel, or the power company needs to check and see if it's their problem. So yeah, that can be very dangerous. But basically, the shield of the cable becomes your neutral conductor.
And Billy asks, can you touch on plenum cable, how it differs and what its purpose is?
Oh, good question. Plenum cable. Back in the 80s, the National Electrical Code was revised in, what was it, Article, was it 820? I'm trying to remember now because I was really heavily involved with some of that back then. And they defined 4 categories of what basically amounts to UL, Underwriters Laboratory listings for drop cables. Or for cables in general used in premises. There was the CATV, CATV-X, I forget, the CATV-R for risers, like elevator shafts, and then there was the plenum-rated cables. And they all had to do with the release of smoke and the ability to propagate flame. The plenum cables usually had a Teflon dielectric and a Teflon jacket, and it was really difficult to put connectors on that cable. But that was used in plenum or air handling spaces where you didn't put the cable in conduit. If you put the cable in conduit, you didn't need to use it. But if the cable was not in conduit, then you have to use the plenum rated cable. It's available. It's expensive because it's typically Teflon that's used for both dielectric and jacket.
Okay. And I think our last question from David again, is there a reason why indoor cables in Europe almost always have a white outer jacket and in the USA a black one?
I think that's probably up to the cable industry. I'm not aware of any standards. Now there might be a standard over in Europe that's under ETSI or something that recommends the jacket color just to differentiate it from what's used outside if it happens to be a separate one. But from a performance perspective, no, there's no reason why you would have to use orange or white or purple or whatever. The color is really irrelevant to the performance of the cable. Other than outside, you probably want to use black because it's more resistant to ultraviolet damage.
And James says, I had one install one time. They gave me a roll of plenum and told me, good luck.
Yeah, that's one of those, may the force be with you.
Yes, quite true.
When I worked for Jones Intercable in the 80s, the corporate office was built with open air handling plenums. And I wired the building. The contractors pulled the cable through, and it was all Teflon rated. And I had to do the connectors at the outlets, and it was so difficult putting those F connectors on that cable because the Teflon is just so rigid. It's just so hard, not very flexible.
Yeah, tough stuff.
All right.
Thanks for all the answers to those questions, Ron. That was awesome.
Do we have a few minutes to go through the manufacturer? Okay, because I think people will find it interesting. I got a few pictures from the folks at Amphenol Broadband Solutions, and thank you to them for that. The rest of this I created some graphics, and I did run this by Tim Cook at Amphenol Broadband, and he said, "Yeah, this is good."
Thank you very much, Amphenol and Tim.
Yes, and some of this is going by my memory of the tours that I've been on of both CommScope, and back in the day it was called Times Fiber Communications, now Amphenol Broadband, but. So I've been through both factories and have seen how coax is made, and to see it made is it's amazing to see it done. So here's how both drop cable and hardline cable are made. So we'll start out with this first graphic here, and there's similarities between the two, but it starts out with a copper-clad center conductor wire. So this comes off of a spool, and I have really simplified this because there are all kinds of guides and pulleys and all kinds of things. And there are also dies that the center conductor passes through to ensure that the outside diameter is consistent. So it's just, we're talking about fractions of a thousandth of an inch just to make sure that it's consistent, and they're measuring it. There's automated laser measuring devices here. So none of that's shown. So the center conductor comes through here, through all that mechanism I just described, goes into the extruder, and the extruder is supplied by a big bin of plastic pellets. So if it's a polyethylene, going to be a polyethylene foam dielectric, they're polyethylene pellets along with some proprietary stuff that goes with that
secret sauce
to manage the chemistry of the dielectric. And then those pellets go into a big extruding screw. And as this screw tapers down in its outside dimensions, it compresses those pellets and they melt. And then it goes through this extruder, and then there's what I don't show here is the gas that is injected into that as the center conductor passes through it. And it's passing through here at a certain speed. And coming out of this right here at the output of the extruder is a really hot dielectric, foam dielectric that's over the center conductor. And it's zipping along, and then it goes through cooling troughs, and they're actually full of water. Huh. So the dielectric passes through this, and there are automated measuring devices and lasers that measure the diameter of the dielectric, and that all feeds back to the speed of the line and a whole bunch of stuff. And then it goes through cooling and drying, and then it's picked up on a big reel. So here you can see these big spools of dielectric over center conductor here, and then the next thing they do.
So that's not the finished product you showed us.
Oh, no.
Okay, that still has a next stage. That looks like white jacketed coax there.
That's just a roll of dielectric over center conductor. That's all cool. That is.
Very cool.
That's all it is. And then the next step is, and they do the same thing for drop cable, by the way. So the next thing is you roll all it up, then you got to start over here. So now you got the center conductor and dielectric gets pulled off the roll. In the case of hardline, it gets pulled through a long, hollow aluminum tube. Okay. And the interesting thing is this process where this reel is and where the take-up reel is in two buildings separated by 1,000 or a couple thousand feet.
Holy
and they got
cow.
These big pipes, and you say, "Oh, wait a minute, what's going on there?" And I remember seeing how the tube was made, because they made their own aluminum tubing, and it's larger diameter than the center conductor and dielectric. And they started out with this billet of aluminum, solid billet of aluminum, of a high-grade aluminum that was, 3-4 feet long and 4, 5, 6 inches in diameter. I don't remember now. And they put this big billet aluminum chunk in this hydraulic press, and then this ram pushed this aluminum, solid aluminum, through dies, and squeezing out of the dies was a hollow tube, and it was so then
cool.
pulled through one of these pipes going to the next building. So now you've got this hollow pipe or hollow tube between the two buildings. And then what they do is they fish the center conductor dielectric back through it, back to the other building. And then at the other building, it goes through a swedger, and that's got a series of dies that slowly reduces. Of course, all this is moving at a certain speed, the diameter of this tube onto the dielectric to a desired diameter. And understand, there's all kinds of automated measurement and stuff going on through all this process. Then what you wind up with here is unjacketed, bare, hardline coax right here. And that gets taken up on a reel. And if you're buying unjacketed bare hardline coax, there's the finished product.
Nice.
It's done. If you want it jacketed,
it's got to go again.
It goes back again.
Oh, man.
And in this case, you've got your bare jacketed coax, goes through all these guides and measuring devices. Then you got the jacket extruder. And in this case, you've got more pellets, and it would probably be, say, polyvinyl chloride, PVC pellets, and some UV inhibitors and other things, more secret sauce stuff that goes in here. Same process with the extruder. They got the screw in there, and these pellets go down, get compressed. They heat up, they melt. And what comes out at this side is now the jacket is over the top of the shield. Goes through more cooling and measurement. And one of the things that they do is a high voltage test to see if there are pinholes in the jacket. And my recollection is that it looked like all these little metal jewelry bead kind of things hanging down, and they had high voltage on them, and if there was a pinhole, it would arc through the jacket. Nice. And they could measure it on the shield, and they could stop the line and say, what's going on? Why are we getting pinholes in the jacket? So here in the picture, you can see this big reel of bare cable being pulled through the jacketing extrusion process. Now with drop cable, the process is very similar, but you start with the center conductor going through the dielectric extrusion, and then it goes through this machine. And here you can see this big reel of tape. So they call it APA tape. I think it's aluminum, polypropylene aluminum, if I remember right. Comes off here, and you can see in the picture on the left this this basically that the foil shield then wraps around the dielectric center conductor combination for the drop cable, and then that in turn passes through the braiding machine. Now, this photograph shows all these reels of this real fine braiding wire, and this was actually developed based on the way rope making machines braid twine into rope. But this is all these spools of the center or the shield wire, and understand that it's not stationary like this. This thing is spinning around really fast, and the dielectric center conductor with the foil on it is going, I think it was going from bottom to top, going up through here. So it's going up, and this thing is wrapping the braid around it, and then that's taken up on a reel, and then it goes through the jacket extruding machine, or it goes back if you're going to add another layer of shield to it. But then it goes through the jacket extruding machine. If it's messenger cable, they extrude the messenger cable in along with it, and then that goes through the cooling process and the high voltage testing and all the other stuff I just described, and is taken up on reels. So
you weren't kidding when you said making coax cable is complicated. It is not a simple manufacturing process.
It's very complicated. So let me stop sharing there. And anyway, so a little over our normal time, but if anybody that's watching this gets a chance to go through the coax manufacturing plant for any of the manufacturers for our industry, Amphenol Broadband or CommScope or Belden, I think, is doing drop cable. Go for it. It is a process, and it's just amazing to watch how this stuff is made.
No, that's very cool. Thanks for sharing that, Ron. Thanks, Amphenol, for sharing the pictures of that. And Peter Whitman says the black ones usually are UV resistance. The white ones are for indoor installations. So this is going back to that question in Europe, why they have white cables.
Yeah, and you could use black cable inside the house. It's done all the time. It's just some operators may prefer to use a lighter colored cable inside the house. That's fine.
So thanks for that answer, Peter. David says, I apologize. A Kelvin connector or 4-wire resistance measurement is done by connecting a constant current source to a cable and measuring the voltage drop. This avoids lead resistance error. So that's the Kelvin.
And it wouldn't surprise me if the lab grade stuff that they're using at the factory is something like this. By the way, when you're using the word Kelvin, other than to describe Lord Kelvin, it is always lowercase. The abbreviation for Kelvin is an uppercase K, but when you're talking about Kelvin, such as thermodynamic temperature, it is a lowercase K. Oh, sorry, that's my editor hat right there.
Yeah. And Grab a Sandwich says thanks. And Grab a Sandwich, I noticed you changed your logo there. You're not a robot. Billy Williams says, thanks, guys. Enjoyed the show. Thanks for that. He says, Ron, sorry for the loss of your dog. He really enjoyed most of the Facebook Geek humor. So,
thanks for both. For those who don't know, we lost our dog earlier this week. We had to take him into the vet. He was really, really sick, and 14 and a half years old, but he brought 14 and a half years of joy. So I'll say to people out there watching, if you've got a furry critter at home, give him an extra hug.
Yeah, so sorry to hear that, Ron. We're
thanks.
Big pet
we're
lovers
big fans
ourselves,
of
and it's really, really tough to lose a pet, lose a family member. Thanks for that. Thanks everyone for all the great comments in the chat room, and please like and subscribe, hit the notification bell so you're notified next time of our upcoming show. It's an end of another show for us. Ron, this was absolutely amazing material.
This was fun. My thanks to all the questions and comments. Appreciate the explanation on the Kelvin measurement. I am familiar with the 4-conductor measurement that was, or the 4-wire measurement that was described, but I had just spaced it. It's called the Kelvin measurement, but that's all right. I'm old, and I can say I'm forgetful.
So, yet again, Ron, I have learned more and more from you in this show. I think people in the chat room got a bunch of good information. And if you have missed us live, please feel free to drop your comments below. We'll do our best to answer them. Ron, thank you again. Another amazing episode. And folks, we will be back next week with John Downey and myself talking more about DOCSIS. So be sure to tune in then. Again, please do subscribe. That just helps us get more viewers and keep on doing what we're doing. So thanks all. Thank you, Ron. Take care. See you next time.
Cheers.